there any questions on the other stuff? Speaking of activities, do you have any specific questions?
On one, just that one that, yeah,
Okay, so lots of ways to go about this. I would start on that side, convert to sines and cosines, and then comment it out. Now, actually, I think I help someone else with this. I think the trick on that one is when you get to a certain step, it's to recognize what you're looking at. And recognize because you end up with all right, read it out to me.
cotangent over 1 minus tangent.
Hold on, wait, start chapter 6. 1, act 2, 1. Read. Number was
4D.
okay, now I'm ready.
Cotangent over 1 minus tangent. And then plus tangent over 1 minus cotangent equals 1 plus cotangent plus tangent.
Okay, so I would definitely start over here. Looks way more complicated without a doubt. Sines and cosines is the first rule. That's definitely where I would start. And then, all right, so again, just going down the rules. So convert to sines and cosines, all right, it's gonna get worse before it gets better. And then what's the second rule? Denominator. Common denominator. I was like, I already see, where am I ultimately looking to go? What's our favorite, like, three little phrases in algebra? Leave it, change it, flip it. All right, basically every time, I mean, algebra. I was like, I know this looks complicated, but I mean, this is an algebra concept. All right, so common denominator. And now let's actually, I'm gonna leave it, change it, flip it individually. So actually I'm doing leave it, change it, flip it on each of these. This is one and this is one. All right, so we have right? Two complex fractions, and I want to do leave it, change it, flip it on each of them because it's just too much to handle at the moment. Okay, so we're back down to a single fraction again, all right, and it looks good. Now what?
The cosine minus sines cancel.
This is across an addition, and you only cancel, right?
Over division, yeah.
Right, over division. If this was a multiply, like that sign would cancel with that and that, like, yeah, if that was a multiply, but this is addition. So again, X's and Y's. Now, actually, as a note, this is one I could have converted to X's and Y's and maybe we could have seen it. But I was like, I feel like we can handle this in this stage. And I didn't want to convert it because it looks like I see something that maybe might help me. I was like, I see sine squared and cosine squared, but in order to get those together, what do I need to do again with my fractions? Common denominator. Now, here's the big trick. Sine theta minus cosine theta, basically y minus x, cosine minus sine, x minus y. These are almost the same. They are different by only what?
Oh, the negative.
A negative. Sine, S-I-G-N. All right, they're off by only a negative. So actually the only difference among these two fractions is this one is missing. What does this one need? This one needs a cosine. What does this one need? A sine. All right, so I'm going to factor a negative. All right, and I'm going to do a common denominator here. And so that's actually, I assume that's the trick, all right, that you're talking about. Because again, I was like, because the temptation, and this is the temptation I see way too often. What again is the fast way to do common denominator? Right? If I just have, whatever, 112 plus 1/56. What's the fast way to do common denominator here?
Just multiply it.
Right, this one I multiply by 56 over 56, this one I multiply by 12 over 12, right, and combine them. But just looking at these, what do these two have in common? What do these two values have in common? What number? Oh, help. That is even. That is even.
So at least a 2.
At least a 2, yes. That's all I was looking for. They might have more in common. I actually don't know. 2 divided into 56 is, let's see, 27. Oh, so that's it. But, no, 28? Oh, so maybe it is more. All right, that doesn't matter though. The point is that the temptation I see way too much is multiply this entire thing into this entire thing into this. And while that does work, you're just down a horrible, horrible path that your algebra now has exploded. All right, we want to keep things small. And so now common denominator, okay, and factor negative. All right, so cosine squared theta. Actually, while we're at it, that just becomes cosine cubed. Sine theta, cosine theta. Cosine theta minus sine theta. All right, I'm pulling that negative all the way out to the front. And just so we can see that it is the same, right? By factoring the negative, that became negative sine plus cosine. So I could just rewrite it the other direction. And probably should have done this earlier, but let's do it now. And could have done that after we converted to sines and cosines, FYI, right? I wanted to, you should get kind of familiar. I mean, sine, cosine, again, variable. Remember, sine of theta is just an unknown, right? Doesn't matter what that unknown is, right? Because at that moment, just sine of theta, I don't have a theta, and there's no identity. Converting it to the trigonometric functions helps us identify identities and such, but doesn't actually help with anything else. As far as all the algebra, it's better this way. So what do we see here? No, absolutely not. Can you cancel across addition? No, no, no.
Different.
Oh, good. What part of the polynomial dance is that?
I don't remember.
Watch the bunny face. All right. Yes, that is a difference of cubes. All right, so same, opposite, always positive. All right, and then x times x times y, and y times y. Now what do we see?
Now, can you cancel?
Yes, why is this different?
Because you don't have the minus in between.
This is an entire expression times this entire expression. This entire expression times this entire expression times this entire expression, right? Everything is being multiplied. Can I cancel that x squared with one of those x's? No, because we have additions, all right, involved in that. But that and that cancel. So we have x squared plus xy plus y squared all over xy. Okay, can't do anything else. Time to go back to sines and cosines. And now this is where establish the identity becomes slightly different than just simplify. I see something here. What do we see? I see the fundamental identity, which means I could turn this into 1. But remember what we're trying to get to, 1 plus tangent plus cotangent. All right. So actually, I don't think I want to do that because of exactly where I want to go. So actually, I'm going to undo the fraction here. I'm going to take the fraction into its individual pieces. And cosine squared divided by sine times cosine leaves cosine theta over sine theta. Sine theta cosine theta divided by sine theta cosine theta is 1. And then sine squared theta divided by sine theta cosine theta leaves me with sine theta over cosine theta. which look at that. There's cotan, 1 and tan. Now, as a note right here, because basically if we would have done the same thing, let's see, we would have gotten 1 plus secant theta cosecant theta. So if I had turned this into the fundamental identity, because I would have had 1 plus sine theta cosine theta, which would have still become that one, but that would have been 1 over this stuff. And while this is a perfectly acceptable and probably the better simplification, this actually established the identity. So I actually needed to get to there. If you didn't see that this becomes this actually I think might be the hardest stage. Remember, what's the other thing we can do? If you get stuck on the left side, flip over to the right side and do a few steps with that. And basically you meet in the middle and then, oh, look, on this side I got this, on this side I got this, then they're equal. All right. The hardest part, okay, 2 hard parts on this one. One is this one.
It's negative.
It's not negative. That is the same thing. And again, these aren't trig. That's not a trig concept. All right? That is algebra. All right. That's what I told you guys like day 1 of the course. What everyone struggles with is not the trig. I was like, that is a slightly new way of thinking, but it's algebra, fundamentals, right? Why did we do algebra for 10 years? Because it keeps coming back, right? And I've always had the argument, oh, I didn't do algebra for 10 years. Yes, you did. Everyone did. If you have a high school diploma, you did algebra for 10 years. All right. So, all right. Then the other trick of this one is right here. All right. And that is recognizing our factoring. Right. That's why I did that little factoring review. All right. Because factoring is just so crucial. All right. It just keeps coming back over and over again. Being able to recognize and look at that and be like, that's a difference of cubes. Oh my God. And the biggest thing is count your terms. And remember, we looked at those, we had those 3 cases. You have 2 terms, some are difference of cubes or difference of squares. You have 3 terms. What do? Diamond. All right. AC diamond, full diamond, partial diamond, either way. You have 4 terms. What do? Grouping. And that's it. All right. And then greatest common factor, which is doesn't matter how many terms you have. All right. So factoring is super crucial because again, in these cases, I was like, we're just trying to get one side equal to the other side. Seems hard, just algebra. And again, could have done this way earlier, kept it as sines and cosines, probably too long, right? Like at this, because I wanted to see if I saw, I'm waiting for those definitions to pop out. And when I have stuff in X's and Y's, I don't see any definitions or identities, all right? X squared plus Y squared, all right? I don't see that that's the fundamental identity, okay, until I get it back here. So, and actually, just as a note, at this stage, I could have broken it up and canceled and shoot, we could have got all the way to the end in X's and Y's. There would have been 2 steps with trig functions, all right? All right, that's a good problem. Like that. That's good stuff.
I fought with that one for a while.
I was like, sorry, see, and now I robbed you of the satisfaction of coming to it on your own.
No, you didn't. I'm good.
All right. As for today. All right, so we want to lecture this, and then what are we doing next class? A learning opportunity. All right, which we have in the form of a quiz, not test, quiz. Right, less threatening. Okay, along these lines, Jada, I love that you always have this up. All right, so along these lines, we're now looking at double angles, so yay! Okay, we're over here, let's see, we're actually, oh my gosh, we're actually gonna get through. She doesn't have a lot of sines and cosines on it? Oh, that's weird. Okay, actually, today and next week, we are going to get through the rest of your cheat sheet, all right? So that sheet has basically everything, all right? The rest of these. Double angles are the big ones. And really, we have it written 4 times here. There's really just 2 of them, okay? Sine 2 theta. Now, here's the big thing. Theta is an angle, remember this. So theta is 30 degrees, Okay? Or actually, let's do, well, 30 just works out too easily. So theta is actually 30 degrees. So 2 times theta is 60 degrees. Let's pretend we didn't know sine of 60 degrees. But what we do know is sine of 30 degrees. Okay? So being able, sine and cosine. So being able to break something that is an unknown into the smaller angles, all right? This again widens our array of possibilities. And so what I was saying is there's actually listed as 4, but these are all just alternate ways of writing the double angle of cosine by using the fundamental identity and plugging it in, right? Cosine squared theta equals 1 minus sine squared theta, and we get this one. Sine squared theta equals 1 minus cosine squared theta, and we get this one. So this is the generic one, and then plugging in the fundamental identity gets these other two. Now again, they're on the cheat sheet, and are all 4 of them on there? Yes, it is. It just says equals, 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 right? So it even has it as one thing, but this first one, all right, is all you need, and then you can just alter it to make the other ones. So it has it written as one big long string of all the equivalencies by plugging in the fundamental identity. So how this helps us is, if I know a trigonometric function equals some ratio, be aware that this is again an angle. This is some angle, 13 degrees. But I don't know what this angle is. All I know is the triangle that creates. So I can't just multiply this by 2. That 2 is 2 times the unknown angle. It's not equivalent to just, pull the 2 out. Okay, it's not like even and odd properties. The only way to do these is to use the double angle. And this opens up our possibilities of more angles we can find with more limited information. But as with everything in trig, what shape do we need to create? A triangle. All right, so notice we have some information here. We have the sine of the angle, but also we are told, all right, the angle at least is in between pi over 2, all right, and pi, which means what quadrant are we in? We are in the second quadrant. So our triangle is this guy. And remember, the angle always comes off the origin. And sine is what over what?
Opposite over hypotenuse.
Opposite over hypotenuse. And so what's our missing side? Oh, yes, it is the adjacent side. I mean, what is the actual number of our missing side? This feels like a special triangle. How does it go? What's the most famous triangle, right triangle? A 3, 4, 5. Is this a 3, 4, 5? This is a 3, 4, 5. Right? Now, if you didn't recognize that's a 3, 4, 5, how can we do it? God bless Pythagorean theorem. All right, every time. Now, here's the other important part. Because we're in quadrant 2, what else do we need to look at with our 3, 4, 5 numbers?
Which ones are negative?
The sign S-I-G-N, right? We need to see if these are positive or negative. Okay, so in quadrant 2, is that 3 a positive? Yes. Is this 4 a positive? No, the X value there, so that is actually a -4. Remember, when we actually do Pythagorean, you would square root the number. When you square root in your calculator, it always spits out the positive, okay? But when you take a square root, there are actually 2 solutions, and that's what we have to be aware of, all right? Your calculator will not catch this, all right? You have to make sure that you draw the triangle and understand that this is the X coordinate, and that is in the negative direction. Okay, so now I have that, so I've made my triangle, and then I can find whatever I'm looking for. This is always the most important part. Draw that triangle. So sine of 2 theta equals 2 sine theta cosine theta using the double angle. And sine theta we already have, 3 over 5. And what is cosine theta?
Negative.
Yeah, just right? It's SOHCAHTOA, right? And it is that simple. And then just for completeness, okay, let's see, 6 times 4, negative 24/5. Now, I typically always use this one because that's the one that I have memorized, right? That is the first one, and the other two are just repeated variations of this. You have the cheat sheet in front of you, just use whichever one is easiest. And we already found both sine and cosine. Okay, so let's see, 16/25 minus 9/25 7 equals 7/25. Beautiful. And so, again, without ever knowing what that angle is, right? Without ever knowing what this angle is, I was able to find not just the original angles, but the double angles as well. And that's the whole concept, right? With just this teeny little piece of info, we could just find tons and tons of stuff. Along those lines, all right, there is also the tangent double angle. So very similar to the product sum or sum difference formula for tangent, right? Which is on the bottom of the left side that I said we don't use very much. We don't use this one very much. Most of the time when we're trying to identify tangent, what's the best thing to do? Sine and cosine, all right? So I put this on here just because this is like one of the singular cases that, oh my gosh, we're going to get to use the sum difference formula for tangent to prove the double angle formula for tangent. And I only put it on there for that reason. So this is the positive version of the sum difference formula for tangent that's right here. Tan 2 theta, which actually equals tan of theta plus theta, right? Because that's what 2 theta is, in order to use the sum difference formula. So when I use the equation right here, I get tan of theta plus tan of theta, 1 minus tan theta times tan theta. Simplify that down, I get 2 tan theta all over 1 minus tan squared theta. Oh, and look. The double angle formula for tangent theta is actually just a special case of the sum difference formula for tan of theta, tan alpha beta, whatever. So just again, that is a straightforward, like using this one. So this one, I definitely don't have memorized. Is this one even on the? Oh, it is. God, that's even more of a waste. That's even just a waste of space on the cheat sheet because this is a special case of this, which is almost never used anyway. So like I said, this is a good starting cheat sheet. There are things that you can do to improve and make your own cheat sheet, and this is one of them, in my opinion. All right, some more identities. This is what your cheat sheet, I think, calls power reducing formulas. But be aware that these are the same thing as the half angle formulas. Look at this. So, all right, the half angle, aka the double angles rewritten. These are all the same formula, right? This is just, if I multiply this by 2 and subtract 1, this is the double angle equation. Then you take a square root and you end up with the half angle or power reducing formulas, all right? So these are all just variations on this very first formula we looked at. And that's always, I want to point that out because look how big this cheat sheet got when this much of it says the exact same thing, all right? And so again, I just want you to be aware of that. All right, but what we can do, what's kind of fun, is with these rewritten double angle formulas, all right, I can establish some identities and kind of mess around. This is actually, and I want to point this out because this is almost one of the very, very few cases where if I come to this side, the more complicated side, which is where we should start, right? We actually not sure where to go. This is one of the few cases where I want to start with this simple side because I can make the simple side expand faster than I can fix the other side. So cosine of the fourth is actually cosine squared squared, right? And we have our formula right there for what cosine squared is, which is again, just the double angle rewritten. And so I can actually expand this and hope that this ends up looking like the other side of the identity. Because it's actually easier to work with this side. And it's easier, and then reminds us of another big algebra principle. The common thing in algebra, I always ask everyone, what do you hate in algebra? What is always causing you the most pain? Anyone know? Fractions, right? Everyone seems to hate fractions. They're just difficult, difficult, difficult. All right, they're just messing everything up I like when everything is in the numerator. The denominator is just killing me. This is another one. Can I get rid of this denominator actually pretty quick? Get rid of is the wrong thing. Can I pull it aside? That is, can I do this? Yeah. Okay. Remember that square is going into both the numerator and the denominator. So I can square the denominator and then just pull it all the way out because it is a common denominator. This only works with common denominators, be aware. Okay. But I was like, I can get that number out of my way immediately. So I'm just left with 1/4 times 1 plus cosine 2 theta quantity squared. And that actually makes my life a lot easier very, very quickly. So I don't have to mess with that thing. I just have to make sure I don't lose it somewhere. And then what do we do with this 1 plus cosine 2 theta squared? How do I simplify that down? What algebraic approach? I always hear you say it, Jada. Not factor. Opposite of factor. FOIL, right? This is FOIL, or AKA box, either way. Okay, so box that out, FOIL that out, whatever you want to do. And then I end up with this guy. So always be sure to check. All right, it's actually looking pretty close to what we were looking for initially. I got a cosine 2 theta. I don't have a cosine 4 theta. Also, right, I didn't have a squared. If I didn't have a squared, that means I need to reduce that down. And once again, that means I want to alternate using the rewritten version of my double angle formula. Okay, now here's a note. Cosine squared, this says cosine squared of theta equals 1 plus cosine 2 theta over 2. For the one that we're about to do, it's cosine squared of 2 theta, which means this becomes what?
4 theta.
4 theta. And it is that simple. And it works in the other direction, all right? That's why they call them power reducing formulas, double angle, half angle. It's all the same thing. It's just, and it's all multiples of 2, all of it, all right? So just make sure that when you adjust this one gets adjusted. If I put a half here, if this is cosine squared of half theta, what is this now? Just theta, right? And we can continue that ad nauseum. All right, I'm gonna break this up because we got a lot going on. All right, and then last up, let's multiply that 1/4 through. And is that what we were looking for? And that is what we were looking for. Oh, good. So, again, just kind of messing around, double, half, all kinds of good stuff. All right, so the half angle formulas, which again, here's our power reducing formulas. And I now literally replaced the theta with theta over 2, alpha over 2, whatever, all right? And it just became alpha, all right? Because it's a 2-to-1 relationship. This is double whatever this is. Because again, these are the double angle formulas just rewritten. We could literally start with the double angle formula. These are actually a little more useful when we take a square root. And it's because, all right, the half angle formulas actually can determine, all right, our triangle or the individual angle. And this sign, notice all these have plus or minus, all right? That sign is determined by what quadrant the half angle is in. All right, so let's look at an example. So I have sine of negative 15 degrees. First, foremost, and always, when I have a negative angle, what should I do?
You pull it out front.
Right, because what's the properties?
I don't remember.
Even and odd, all right? Even and odd properties, you always should use first to deal with negative angles. The only things, remember, they don't work on is inverse cosine and inverse secant. Otherwise, even and odd properties, you should always deal with that first. Specifically, sine is odd, which this now becomes negative sine of 15 degrees. All right, so already that's fantastic news. So I can pull that negative all the way to the front. So what this means, alpha over 2 is 15 degrees. That means my angle alpha is then what angle?
Thirty.
30 degrees. So, and this brings up the simple concept. Do we know the trigonometric functions for 15 degrees? No. Do we know them for 30 degrees? Yes. So it's the concept that we're getting back to our three main angles, okay? It's just one more way to get an exact solution of those three main angles. And we can now do more and more of them. The sum difference formula can get there. These half angle or power reducing formulas can get us there. Okay, the other thing we need to determine, okay, 15 degrees. What quadrant is 15 degrees in? The first. All right, and this is what this little note here is. This sign is determined by the quadrant of the first angle. So 15 degrees is in quadrant 1. In quad 1, the sign is positive, or negative. Positive. Everything is positive. It's quadrant 1. That's our favorite quadrant. Okay, is positive. All right, so use positive of half angle formula. And then, all right, once I've adjusted, I identified as positive. So then cosine of 30 degrees is √3/2 over 2. And then it's just a matter of reducing down this fraction. Our work is basically done. All right, but let's see, we gotta do some common denominators here. Which gives us, all right, with some leave it, change it, flip it. And we end up now. Is this a pretty number? No, this is a radical inside a radical. Okay. Algebraically, though, we can't get this any cleaner. This is an exact solution. All right. And I mean, I only have 2s and 3s here. Okay. So this is an exact solution, but that's as good as it gets. And then here's the other thing. All right. Don't forget to use your calculator to check. All right. Your calculator will do sine of 15 degrees. Right. Put in sine of 15 degrees. It spits out a decimal. Then evaluate this in your calculator. If those two numbers are the same, you got it right. I mean, your calculator is there to help. All right. Everything we do that we're going to be doing for a bit longer is exact solutions. All right. No approximate, not yet. All right. Let's do another one. So I have cosine of -3/5. All right. The angle is between pi and 3π/2. Find the exact value of alpha over 2. Okay, so we can do this in a couple pieces. Let's start with our main triangle. It's always the best place. Pi to 3π/2. What quadrant are we in? Quadrant 3. All right. Cosine is adjacent over hypotenuse. And once again, I think I recognize the triangle. What is it? It's a 3, 4, 5. Oh, just that happens, right? And then we need to identify the sign. So it already said cosine was negative, right? -3/5. Okay. In quadrant 3, all right? Actually, both the 3 and the 4 are what? Negative. And then other big note, you guys might already know. Is the hypotenuse, is this negative? Is it ever negative? No. Okay, the hypotenuse is always positive. Remember, it represents a distance. Okay, so the hypotenuse is always the positive value. Okay, good. So I have, oh, sorry, I'm calling this alpha, not theta. All right, so I have my triangle for alpha. Now, we need a couple things. We need to identify the sine of the half angle, which means we need to identify the quadrant of the half angle. Now, the best way to do this, I was told the angle exists between pi and 3 pi over 2. Well, I'm trying to identify stuff for the half angle, so take this whole thing, divide it by 2. That gives me pi over 2 less than alpha over 2 less than 3 pi over 2 divided by 2 is 3 pi over 4. So the half angle is between pi over 2 and 3 pi over 4. What quadrant is that?
Second.
The second. So actually the half angle is over here. Okay. It's somewhere, the angle is somewhere between here and here. Here's 3 pi over 4. And here's pi over 2. All right, so the half angle is a bit different. We are specifically looking for tangent. All right. In quad 2, tangent is positive or negative? Negative. All right. So tangent is negative here, which means we're going to use the negative of that half angle value. And then once again, just a matter of actually plugging in. So actually cosine, and we didn't actually even barely need to create our original triangle here because it gave us cosine. I was like, I didn't even need to find sine or anything else. And again, just remember, this is cosine of alpha. So cosine of alpha is -3/5. Bless you. And then once again, just a matter of simplifying this thing down. Five 8/5 over 2/5. Oh man, that one came out nice. All right. Usually the trickiest part here is getting that sign. Getting that sign, because you have to identify the quadrant of the half angle. And that's the thing that people mess up. Notice, all right, in this first example, the half angle is 15 degrees. All right. Oh, geez, we forgot that negative at the end. Oops. Speaking of, all right, because it was actually negative sine of 15 degrees. But the quadrant of the half angle is quadrant 1. The full angle is quadrant 1. So everything was positive there. This one, all right, the full angle is quadrant 3, but the half angle is in quadrant 2. All right, and so that's the trick in identifying what is the quadrant of the half angle. And then as a note, so on your notes here, I say, oh, one more identity. There's another way, all right, to do the tangent of the half angle. It's just sine over 1 plus cosine or vice versa, basically using the conjugate to get between those two. However, this one is actually an easier formula because, once again, sine, right? I have cosine. Tangent is sine over cosine. That is sine divided by the cosine. If you put this one in and this one in, leave it, change it, flip it, you end up with this. So once again, you actually only need these two. All right. Okay, so product to sum, sum to product rules. These are the formulas that even I don't have memorized. And I don't have them memorized mostly because the proof of how to create these is the sum difference equations. So I'm going to write out the definition of cosine alpha minus beta, the sum difference formulas. All right, so that's just writing out the definition. Literally, that's all this is. This is the definition of the difference with cosine. This is the definition of the sum with cosine. Now I'm going to do something we do very, very often in math. I'm going to add two equations together. On the left side, do I want to add these or subtract these? No, let's subtract them. Same thing. Add two equations, subtract two equations. All right. On the right side, so that negative, this becomes now negative. This goes away. All right, because I'm trying to get to one of these specifically. So that is cosine alpha beta minus cosine alpha beta, that's gone. Then I have sine alpha beta, negative, negative, plus sine alpha beta. In order to make this more clear, I'm subtracting that one only. So that ends up with 2 sine alpha sine beta. Then I can divide this whole thing by 2. And I end up with 1/2 cosine alpha minus beta minus cosine alpha plus beta equals sine alpha sine beta. So again, all I did is just add two equations or whatever, add negatively, two equations. And notice, all right, what we ended up with. The first, all right, product to sum is exactly this definition. Now, by adding combinations of the other sum difference formulas, I could get the other ones. Now, these ones, even I have these ones written down. These are things that just go on your cheat sheet and you just use them when appropriate. And here's when they're appropriate. And it's almost always the same instructions. All right, express this only as a product or difference of signs. And most of the time, it's even clearer than that. It says, take this and convert the product to a sum, or convert the sum to a product, or convert this to some sum or difference. It's always mentioning products to sums in some regard. And the only thing we need to do here is just identify which one is alpha and which one is beta, and then make sure that you're plugging it in appropriately. So looking at our equations, I have sine 3 theta, cosine 5 theta. So sine times cosine, right? That one's sine times sine. That one's cosine times cosine. Oh, look, there's sine times cosine. So it means I'm going to use this one, and the sine is alpha and the cosine is beta. And then plug it in to our equation. And simplify down. And then one other thing again, sine of negative 2 theta. What's sine of negative 2 theta become? Right, even and odd properties. Wherever and whenever possible, all right, you should never have a negative angle unless you literally can't avoid it. Right, and like I said, the only case where we have to deal with it is inverse cosine and inverse secant, and that's pretty rare. All right, so basically that's what we had, 12, 2 out of 1/6 of the time. That's it. Okay, and again, using the properties, pretty simple. Put them in, identify your alpha, identify your beta, simplify down. Along the other lines, sum to product, product to sum. As a note, these are exactly what we just had. The only difference is, instead of this being alpha minus beta, they changed these ones to like summations. But it's just rewriting the same formula. And see, look, here's the directions. Express as only a product. So if you have a sum and it says do only a product, by definition, that's sum to product, product to sum. And once again, so in this one, all right, I have cosine plus cosine, which means which of those four am I using? The third one, right? That means I'm going to use this guy. All you have to do, identify alpha again, identify beta, and plug and chug. And again, not a lot going along. I see people really struggle with these. And again, I think just you're overthinking it. This is like as plug and chug formulaic as it gets. All right. So on these ones, the directions are almost always the same. Turn into a product, turn into a sum. Use the definitions. Even I use those formulas. And that encompasses the bottom, like 8 formulas on your cheat sheet. All right, let's establish some identities. Time we got? Okay, we got enough time for one. All right, so I got A, B, C. All right, let's start with A. Gosh, what side do you think we should start on? Yeah, I think probably the left, right? Oh, could someone open the door for Jada?
Thank you.
Okay, so I got the left side here. What do we think we should do? Common denominator, right? Again, go down the list. What's step 1? Technique 1, whatever.
Sine, cosine.
Sine, cosine, done. Second one, common denominator. And then look, does it seem like it's reasonable to create a common denominator? I would say absolutely. And finally, I just warned you 50 times about it. What do we get to do in this case? We kept warning you against this, doing this technique in common denominator. But we actually get to do it here. What do I multiply this one by? This fraction, in order to create a common denominator, what do I multiply it by? The other one. And guess what we get to multiply that one by? This one. All right, so I just said don't do that a bunch, right? And this is actually the case where I get to do it. All right. So this one gets to be multiplied by cosine theta plus sine theta over cosine theta plus sine theta. This one gets to be multiplied by cosine theta minus sine theta over cosine theta minus sine theta. Because there is no other denominator to make here. All right, I have a subtraction and addition in the denominator, which means I have to multiply it by. And in this case, we're doing common denominator while kind of simultaneously doing conjugate, right? Because this is the opposite sign on both of them too. And that's always good news doing conjugate with sines and cosines because I'm going to create the fundamental identity. Okay, I didn't box these out, but this is a perfect square trinomial in the numerator and a difference of squares in the denominator, right? So those are kind of easy to recognize multiples. What are we trying to get to? 2 tan 2. Okay, we got a long way to go. Okay, let's put it all under the same denominator and see what happens. Actually, so I don't have to write another step. I have a negative out here. So that becomes a positive, that becomes a negative, that becomes a positive, that becomes a negative, right? Just gonna rainbow that negative through. All right, save myself a step from writing a whole new step. So I have cosine squared theta minus cosine squared theta, that goes away. All right, I have 2 sine theta cosine theta plus 2 sine theta cosine theta. So that becomes 4 sine theta cosine theta. And then I have positive sine squared theta minus sine squared theta. Oh, look, that goes away. All right, so that was pretty nice. That means all that's left in the numerator is that. And in the denominator, so actually that's simplified pretty quick. And then, does anything jump out at anyone? What jumps out at you, Brenna?
It's not quite the fundamental identity, but
Nope, it is not quite the fundamental identity. But something that is not quite the fundamental identity, we literally talked about today. That is not quite the fundamental identity. But that is a double angle, right? These are alterations of that double angle. And oh, I think actually both those double angles kind of look like they should be coming along. And also, again, this is an established the identity, so I know the solution. There's a double angle in the solution. All right, so there's a double angle in the solution, which means I need to be headed towards double angles. So I can actually rewrite this as 2 times 2 sine theta cosine theta all over, I'm just gonna leave this one, cosine squared theta minus sine squared theta. Definition. Sine 2 theta equals 2 sine theta cosine theta. And cosine 2 theta equals cosine squared theta minus sine squared theta. So that one becomes 2 times sine 2 theta all over cosine 2 theta. Sine over cosine is, of course, tangent. Oh, look at that. That was beautiful. And we got time for one more. Are we okay? All right. Doubling, just more formulas. We just keep looking at that cheat sheet. All right, what's the matter, Kaylee?
It's just head is spinning.
This is good stuff. I love these trick.
A lot of stuff.
It fits on one side. I just said how repeated that sheet is. It has one cheat sheet. Just look at the picture, and I was like, you can condense that down to like this much. Okay. All right, for part B here, I have sine of a bunch of stuff equals cosine of a bunch of stuff. Which side should we start on?
Doesn't really matter, does it?
No, it does not, because they're basically the same. All right, so let's just start on the left side. We like to go left to right. So sine theta, sine 3 theta, fine. Plus, yeah. Okay. So, trying to convert a bunch of sines to a bunch of cosines. Does something look, is there something here that maybe it looks like we can use? Notice our values. 1 theta, 3 theta, 5 theta. Are those double or halves? Is that double angle stuff or half angle stuff? No, because why? It's not a multiple of what? 2. All right, which means we don't use any of those, and that's how you start recognizing, right? So none of those double angle, none of those power reducing. What's left?
Sum of product.
Sum of product, product to sum. Okay? Usually with all algebra, where do you start with the parentheses? Right, you start outside the parentheses? Inside. So let's start with this deep inside piece and let's go, right? I have a sum there, so I want to use my sum to product formulas. All right, and specifically, all right, I have sine plus sine, all right, which means actually I'm going to use the first one. And again, just means identify alpha, identify beta, alpha 3 theta, beta 5 theta, or vice versa. And as a note, I'm pulling out the inside, right? I'm just taking it, so I still have that sine theta out front. Just pulling out to use the definition here. I'll simplify this in and then put it back into my equation. All right, so that simplifies me down to 2 sine 4 theta cosine of negative theta. And once again, cosine even or odd? Odd's a good guess because most things are odd, but it's even. I was like, the odds were definitely in your favor. 8 out of the 12 are odd. 2 out of 12 are even. 2 out of 12 are neither. So, all right, cosine is even. And even should be your favorite because what do you do with the negative with even? Drop it. Bye-bye. Okay, so now let's plug that back in. All right, so once again, we started with sine theta equals sine of 3 theta plus sine of 5 theta. So this now becomes sine of theta times 2 sine 4 theta cosine of theta. All right, so, all right, just writing it out, right, and rearranging. And this is when it comes to, I want to remember where I'm going. All right, I was trying to convert all this sine stuff to cosine stuff. So actually, I'm going to write it in one more different order. So just reordering it again. This is the same thing. Because I got my cosine, so I finally have a cosine. I did all that and I have a cosine. So I have sine theta, sine 4 theta. All right, so looking at where we were going again. I have a cosine theta, so I do need that. But then look at cosine 3 theta minus cosine of 5 theta. So if that's where I'm going, and this is what I currently have, what springs to mind?
Product sum.
The other way. I have a product, now I need a sum. Your head seems fine. I was like, that's the hardest part, is what do we do now? All right, so product to sum. So again, I'm gonna grab the inside, I'm gonna ignore the outside. Sine theta, sine 4 theta equals. All right, using the product to sum equation. Oh, we should have a half in there, right? Yeah, half. Then we have a 2.5, and this becomes cosine of theta times cosine 3 theta minus cosine 5 theta. And I believe that is what we were looking for. See? It's good stuff. All right. All right. We have a little quiz next time. We'll resume this a week from today. And we'll continue on. There's so much good stuff. The problem will go. There's just one from the activity, that's all. I was just doing a problem off the activity, the Galen knows. Is it negative 5/6? Inverse cosine isn't ever negative, is it? I think it is.
No, this is 5/6.
Yeah, so it's the positive, okay. Because the graph of what inverse cosine is, it's only from the graph of inverse cosine. basically it's only 0 to pi. So you can never, cosine is the hard one. That's what I was saying. So the graph, right? Start high and I'm gonna end down here. So this is cosine, y equals cosine of x from 0 to pi. And that's the only option for inverse cosine.
So my final fiscals whatever will always be positive.
Yes, if it's inverse cosine, it's always positive. And this is the hardest one. That's what I was saying. Inverse cosine is not odd, it's not even, it's neither, which means you have to deal with that stupid negative. This is the toughest case, which is why I put it on here. So I wanted you to make sure you understood that concept.
And this, how do I do this? I don't understand. How do I
Okay,
do
so
this?
start with- Yeah, so start with the inside, good. Okay, and this isn't on the unit circle, right? This one you just gotta create, just create the triangle. Okay, so hold on. Back here, let theta equal that, sine, yes, excellent. So right here, you got it. That's that part. Okay, now create the triangle.
Do I have to do like side and same to the rest?
The rest, you mean the one missing side? Yes, there's only one thing missing. And then,
I can plug it in there.
and then, yeah, so then look, secant equals theta, right? Secant equals theta, which means, okay, yeah, you don't need that, which is 1 over cosine of theta. And then as soon as you find this, you're gonna put, guess what cosine of theta is? It's gonna be that over that.
You might be able to do it.
Is that right there?
There?
Yes. Yeah.
No, I was just noticing something. I did 8, you do like layers.
So I do adjacent opposite hypotenuse. I do AOH because we're in trig. But it's a squared plus b squared plus c squared, yeah. So it doesn't matter. That is x. Now solve for it. X squared plus like 2 root 5 squared
Wow.
equals 5 squared. So remember
Get rid of that.
the 2, so square root of 5 squared is 5, but the 2 also gets squared, so 2 squared is, so you have 4 times, which is 25. That one's easy. That one's a new one. Right?
Wait, so now we're gonna put this in here.
Yeah. So what's cosine of theta? Given our triangle. Uh, What did you write there?
I was gonna do root 5 over 5.
Yes. Oh, it's not, oh, you wrote cos. It's not cos, it's root 5 over 5. Cosine of theta is root 5 over 5.
Oh, so it's telling me this is.
It's not cosine of that, it's just root 5 over 5, and then leave it, change it, flip it, becomes. Five over root 5. Depends, but I was like, you can leave it like that, or you can check what the solution has.
I think the solution was root 5.
Yeah, because actually when you rationalize this, it just becomes root 5, right? You can leave it like this, I don't care, as long as you understand that this is this. Make the triangle, everything is make the triangle.
Yeah, I was stuck at this. Didn't know.
Yeah, no, and this is the part that everyone skips. Well, once you're right here, then you make the triangle.
It's not on the user, but you have to make a triangle.
Absolutely, 100%. There is no other way. And technically, the unicircle is just a shortcut from making a triangle. I was like, you can always make the triangle. The unit circle is the shortcut. So we don't have to make the triangle every single time because we would keep making triangles that always look like this. So we would keep making triangles that ended up like that. Or wait, not that. One, three, two. Yeah. So our triangle would keep looking, we would keep having the same triangles over and over again. That's all the unit circle is. It's a shortcut to the two most common triangles, 30, 60, 90 and 45, 45, 90.
Well, you keep working on this.
Yep, keep plugging away. That's the best thing you can do.